Okay, everybody. So what we're going to be looking at today is section 6.6 in your book, surface integrals. Now, surface integrals are going to be a lot like line integrals, but they're not. They're surface integrals, but a lot will be similar, right? So, uh, surface integrals have a lot in common with line integrals. And in fact, even though I want this out of the way, I will write some of the similarities here. So like, for example, if I say like line integrals here, and I put surface integrals here, and just kind of list the equivalent stuff for both of them. So like, this is going to be actually take up a lot of space, I think. So just move this way down here. Okay, so like on a line integral, right? You can parameterize a curve. That's one thing you have to do, right? You parameterize a curve usually with one parameter, right? Usually t. Well, on a surface integral, you parameterize a surface with two parameters, usually u and v. Doesn't have to be, but often u and v. And this is usually t. Okay? Now, then you were able to do like the most basic line integral was actually arc length. So the most basic integral is arc length, and it was an integral over a curve of, and it was just ds, where ds was something, right? Well, what you're going to have for surface integrals is the basic integral is going to be surface area. So you'd have an integral over a surface of d, and we're actually going to use a capital S there, which is a little bit confusing that we have a capital S here and a little s here, but there you go. So this is going to be a length because it's the length of a curve, and this is an area because it's a area of a surface. And then from there, with line integrals, we moved into line integrals of functions, so scalar functions, right? So then you did line integral of a scalar function, which was just a line integral over c of f ds, right? Well, we're going to have the same thing here. We're going to have a line integral, sorry, a surface integral over a surface. Um, so what's that look like? I just want to copy their notation exactly, so that's why I'm scrolling through here. Blah, 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 blah. Yeah, okay, they don't do anything special. They do use a double integral symbol here, though, so I'll switch it to that. So we have a surface integral of a scalar function. And it would be a double integral over a surface, and then they say f ds. And then finally, you could do a line integral of a vector field, right? Which was an integral over c, and there were different ones, but you could write like uh, f dot t ds or f dot in ds, depending on what kind you were doing. And what we're going to have here, if I scroll, um, where did they define this? Yeah. Then we're going to have a surface integral of a vector field. And they write f dot ds or f dot in ds. So the different f's. Okay, so you can see that there's like a lot of similarities in the notation and how we do these things. Okay, so a lot of this we're going to have to do pretty quickly because this is all in one section. Um, yeah, so we're going to go ahead and get started now. But you can see that there's a lot in common. I guess we'll just start this on the next page. So surface parameterizations. So you know that curves are parameterized with one parameter. So recall curves usually, not usually, they have one parameter, usually t. We just talked about that. Okay. Surfaces are parameterized with two parameters because it's a two-dimensional object. So there's different ways to do this depending on what kind of surface you're looking at. So here's an example. Um, so our first thing we're going to do is we're going to do parameterize a surface given as like z equals uh, some function of x and y, right? All you do is this. Um, just use the parameterization. So your x of t, nope. Your x could just be x or u. Your y could just be y or v if you want to use a different variable. And then your z is just f of uv. So there's no work, right? So there's no work. Even this works. X equals x, y equals y, z equals f of xy, right? So you don't even need to change the variable names. So like here's an example from your homework. This is the first homework problem you have from this section, or at least just the first one I had. Parameterize, that says pain. Parameterize negative 20x minus 6y plus 2z equals negative 18. So this is a plane. Okay, so how are we going to do it? Well, we can do this. So we can just say, we're going to use u's and v's. So let's just let x equal u. Let's let y equal v. And then what would z equal? Well, you can just figure it out, right? Like if you just make those replacements here, you have negative 20u minus 6v plus 2z equals negative 18. Move the u's and the v's over, you have 2z equals negative 18 plus 20u plus 6v, and then divide everything by 2, and you get z equals negative 9 plus 10u plus 3v. Negative 9 plus 10u plus 3v. So that could be your parameterization. Yeah. And then they actually list it this way. Um, so the actual boxed answer is this. Answer, they say R of UV is vector UV negative 9 plus 10U plus 3V. Done. Okay, so that's going to be the easiest type of parameterizing you have to do. Um, the point is that your X, your Y, and your Z components all need to only have two variables in here. Any surface will it'll be possible to do that, right? So the point is this should contain two variables only, which are your parameters. Okay, so it's the same as parameterizing a curve, but a little bit trickier because there's two to worry about. Let's instructor cheat, go to the next question. Okay, they're already into surface integrals. Um, so awesome, I guess. Let me skip by this one actually, and let's do another parameterization problem. Okay, yeah, so hmm, okay, that's complicated. So anyway, let's continue on here. Let's do another parameterization problem. Uh, Scrolling to find one before we do integrals. Yeah, okay. So let's do this. So I'm gonna call this parameterize a surface with x squared plus y squared in it. Now, this is not like a hard and fast rule for how to do this, but this is just going to be a convenient thing to think about. Um, so whenever you see an x squared plus y squared in your problem, then when you see that, a convenient way to start is with um, x equals v cosine uh, like v cosine u, y equals v sine u. Now that's not again a hard and fast rule, but that's just kind of that might help. Okay, and so an example where that would help would be something like this. Um, so example, give a parameterization for x squared plus y squared equals z squared. Okay. Now this is a cone, and so it looks like. Come on. Okay. So this is a cone like this, but how would you parameterize it? And so again, not a bad way to start would be with this. So if we try x equals v cosine theta, y equals v sine theta, then, well, first of all, you're two-thirds done, but then what you get if you substitute those into the equation is v cosine theta squared plus, oh, I shouldn't have done that, sorry. We change those to u's. U. I mean, you could use theta as your parameter, but it gets confusing to do that because you're used to seeing theta as meaning polar coordinates. And these are not polar coordinates. This is a parameterization of a surface. So I'm going to try this. V cosine u plus v sine u squared equals z squared. And this is, of course, v squared cosine squared u plus v squared sine squared u equals z squared. But then you use your trig identity that sine squared plus cosine squared is 1. So this adds up just to v squared. And so you get z squared equals v squared, or how about just, z equals v? Maybe that'll work. So then that tells you that we just add that to our list. So for our parameterization, we could use x equals v cosine u, y equals v sine u, z equals v. That could be a parameterization of this cone. So that kind of helped us. But, it's not like a, I don't know, foregone conclusion, I guess. Um, so, yeah. So that kind of helps. But they're a little bit tricky. Sometimes you might have to look up like the type of surface and see what the best way to parameterize it is. Hopefully, a lot of them can be done with this first method here, right? Because z equals something is usually how they're given to you. We could have done that here as well, by the way, right? We could have used, you could have just square rooted here and had z equals plus or minus square root x squared plus y squared. And then you would have had separate parameterizations for the top and the bottom because of the plus or minus, but it still would have worked. Anyway, I think that's about all we're going to say about parameterizing that surface. Okay. So then what we want to get into is, well, first of all, the idea of a smooth surface. And let us talk about it. I'm going to post the book's definition of this if I could find it. Yep, right here. It's down a little bit. So this is smooth parameterizations. All right. So this is going to be smooth, like the same idea as smooth for a curve, right? No sharp corners. Um, so first of all, they give you this definition for regular parameterization. And so they say that it's a regular parameterization if RU cross RV is not zero, okay, for a point in the domain. Okay, and I'll talk about that in a second. And then so this is assuming your parameterization is U's and V's, U's and V's, U's and V's, right? So like what we've already done. Um, Now then, they say that that's a regular parameterization. Now look down here, and it says a surface parameterization RUV, XUV, YUV, ZUV, same as this, is smooth if vector RU cross RV, this is also RU cross RV, is not zero for any choice of U and V in the domain, is not zero for point UV in the domain. So, you know, regular parameterization will be like a smooth parameterization. Okay. Um, and the idea here is really this. Uh, Resulting curve should have no sharp corners. Now, the reason this not being zero stops you from having sharp corners is because if you take your surface, which I'll just draw like a surface here, okay, right? So if you divide your surface up like this, and you look at one of these little boxes here, so let me just fill in one of these boxes, and then you take it on the outside and we look at it, then remember that um, basically RU is going to be like a vector like this, and RV is going to be a vector like this. So what you're going to have is like a little flat, little, not a rectangle, but like a little parallelogram. But the point is that it's flat. So if you take a bunch of these little flat rectangles and you put them next to each other, then you get a nice smooth curve. But if one of these shrinks to zero in length, then maybe it wouldn't be a nice smooth transition anymore. There could be a sharp corner at that point. Um, so like, so this would be smooth. But if you had a pointy bit on your surface, right? Then what happens, like in a little section down here, is that where that point is, that shrinks to zero. So you have like your, like maybe this could still be your RV, but maybe this is your RU. And so where that point happens, one of these sides can shrink to zero, and then that's how you end up with a point on your shape. Okay, so that's kind of the idea. So it has to do with the derivatives. Derivative RU cross RV can't be zero, or bad things happen. Okay. Um, Also, again, you do want to keep in mind that no sharp corners, because your homework does give you some graphs and then asks you which one has sharp corners. And they give you a torus and a sphere and an ellipsoid and then something with pointy bits. So the pointy bit is not smooth. So it's exactly what you think it is. Not smooth is not smooth. Um, Excuse me. Select your answer. Okay, well, all right. So anyway, enough of that. Let's talk about surface area now. How are we going to calculate surface areas here? Let me see if I have a picture. Um, yes, I do. I'll just give us the definitions. So actually, let me move this down. This up here. So after we parameterize a surface, we can calculate the surface area of the surface. So that's our first task. The way you're going to do it is, let me move this out of the way. The way we're going to do it is you're going to start with the surface. So step one, You've got, it's fine. Stop making, let me draw a curved line. Okay, you did. Thank you. I appreciate that. Okay, so you have a surface, R of UV, right? That's how we're parameterizing it. After you parameterize it, then what you're going to do is you're going to divide it up into these little sections, right? We can see that area is just um, the sum of all of those little boxes that I drew, right? Like the ones that I just shaded, like this, right? If you added up the area of all of those, you would get the area of the whole thing. So you get area technically approximately the sum of a bunch of those. And so we're going to say ds where, well, what are the ds's? So we need to know what the area of one of these little rectangles is, basically. And so what's going on here is they are telling us what those are. Um, so they've got this picture right here. And so what they're saying is, get a different color. So what they're saying here is you've got one of these little pieces here. Oops, didn't draw that successfully. But you've got one of these little pieces here. Now that is not a parallelogram, but it's almost a parallelogram. And the length of the sides are like this one and this one. That's basically the same. So they're saying that you can calculate, at least estimate, the area of this shape just as the area of the parallelogram that they drew, right? And you can see that those areas are approximately um, the same, okay? But then how would you do that? Well, what you'd have to do is they calculate this TU, which is the derivative of x with respect to u, y with respect to u, z with respect to u. That's from the parameterization. TV, that's xv, yv, zv. And those are going to give you the length of these sides. Now, on its own, that's not the length of the side because um, depending on what parameterization you use, um, right? Like depending on the parameterization you use, these things might have to be scaled, and so they have to be scaled by this, the delta v and the delta u. So um, some scaling factor, right? So what we're saying, like this is hard to see, but I think I can draw it. Uh, I definitely can't. I lied, but I tried. So the idea is down here in this plane, um, like this might be like a delta U and this might be like a delta V. And then up here, right, like you have this right above that. And so obviously this area is not going to be the same as this area, even if this is right above it because it's tilted. So like one of these sides is like what we call the TU. Is that the right one? I think that's the right one. But it's scaled by however big this is. Because if you made this bigger, you'd make this bigger, but by how much? And then same with the delta V. If you make this side bigger, then you would make this side bigger. And so I'll draw it over here though. It's also delta U. So something like that. So that's what's going on is from a change in the U and the V, you're calculating the area, the change, the size of the area. So from the area of this to the area of this. And it's calculated, well, with these two sides that they've labeled here. Okay, it's similar to what we did for arc length, but a little bit different. Okay, point is that once you get down to it, our integral is going to be defined this way, where this entire thing here, this is your um, d capital S. Okay, so that's your d capital S. So um, the double integral of ds is going to be double integral of this thing tu cross dv uh, dA. Okay, and then this is going to be some region in the xy plane. So this is just a regular double integral. This is a surface integral. Okay, now if you are asking yourself, why is there a cross product? That's because this is a parallelogram. So just recall, right? If you put like an A there and you put like a B there, then the area of the parallelogram is magnitude of A cross B. So once they've decided that this is T delta V and this is T du delta U, then you just do the cross product between these two vectors in order to get the area here. So then they have like the sum over, I and J of magnitude TV delta V cross TU delta U, uh, which is, oops, TV cross TU and then delta V delta U. And then they turn that into an integral. And when you turn it into an integral, then, the deltas turn into Ds. Okay, so I mean, that's as much derivation of this as we're going to do. The main thing is that you've got the definition at some point. You have your parameterization here, parameter domain here, and this is a double integral that you're going to calculate. So to calculate a surface integral, surface area here, then this is the integral that you calculate. Also, I'm going to write it here in case you see it here. ds is this thing, tu cross dv dA. Okay, so that's your definition of surface area. Okay, so let me see if I can find an example of calculating a surface area. They've got kind I don't want to see. Oh, we're going to do one more parameterization actually. So before we do one of these, oops, forgot. So this is going to be a parameterization of a surface of revolution or solid of revolution. Surface of revolution, I guess. So I think I have a picture. Hopefully. Yeah, I do. Yeah. So we're not ready to find the area yet. So we will find the area in a little bit, but we're not doing the area yet. We're going to talk about like how do you actually parameterize this. Okay. So you've seen these in Calculus 1, you should have, but the idea is you take a curve, right? You have a curve, some shape. I'll draw a different shape. like this. So y equals f of x. And then you rotate it around an axis. I'm going to rotate this around the x-axis. And then what happens is if you rotate the curve in like 3D space around the x-axis, then you get like a shape like this. It turns into a bowl, right? Does that make sense? I hope that makes sense. Um, so that's what's going on here. They're taking a curve, a simple curve, y equals x squared, and then they're rotating it around the axis to get this. And there's a specific way you can parameterize it. Um, and that's what you would want to know. Scrolling down to it. Do not see it. Yeah. Okay. So here's the punchline. When y equals f of x, uh, for let's just say a less than x less than b is rotated around the x-axis, the parameterization of the resulting surface is, so here's the idea. So take a point here, right? Like if you take a point right here and you figure out this distance, that color is not going to work right there. Will this one work? That's a little bit easier. So like this distance, right? If you pick this x value, of course, that's y equals x squared. But then if you use that as a radius and you wanted to take all of the points around the circle with the that had this radius, then what you would do is you would have x equals like t, for example, and then what you would do is your y and your z would both be something like this. Like, I'll use x here. Um, X would be like x squared cosine theta, y squared sine theta. And then um, if you take these, like y squared plus z squared would is gonna, I wrote this wrong. If you take y squared plus z squared and you add those together, what you're going to get is simply x squared for this distance. So like all of the points that are this exact distance, but in 3 dimensions around that point are given this way. And I know that that's confusing the way I just said it, but I will say it this way. So when you have this situation, y equals f of x, and you want to rotate that around the x-axis, for the parameterization, you can simply use like x equals x if you want, or t. And then for y and for z, previously y was f of x. Your new y is going to be f of x cosine theta or cosine t. I'll do theta. And then your z is going to be f of x uh, sine theta. And so that's just the parameterization you're going to use as a quick way to do this without thinking too hard. Um, so for this example, for y equals x squared, you just use x equals x, y equals x squared, because that's the function, cosine theta, z equals x squared, sine theta. And that will work for your parameterization. Okay, so that's just a way to parameterize this kind of situation. Um, whenever you've got a surface of revolution. Okay, let's actually do a surface integral now, actually surface area to start with. So let's do an integral basically. Our first integral problem. Find the surface area of the portion of the plane z equals, hey, they're being nice to us, negative 4x plus 5y minus 5 above, and then they give us a region in the xy plane, 0 less than x less than 3, 0 less than y less than 2. Okay. Now, I'm not going to draw this plane properly. Okay, so this is going to be a bad picture of the plane. And the reason I'm going to do a bad picture of the plane instead of a good picture of the plane is I just want to draw the plane above that rectangle that they gave us, even though it probably is not. Okay, so I'm going to draw it in the wrong place. So if I've got x here and y here, so basically your region here, this is your region that you're integrating over. This D. Okay, so like x is between 0 and 3, so 1, 2, 3. Y is between 0 and 2, so 1, 2. So you've got a rectangle. I mean, it doesn't really look like a rectangle because I drew it sloppy, but you've got a rectangle in the xy plane. Okay. Now, above that, or below that, actually, it doesn't really matter, you have this plane. Now, this plane is not going to be level, right? It's tilted in some manner. So, because of that, again, I'm not drawing the correct plane, but you've got some kind of plane in space above that. And if you come up here, then these corners are going to end up somewhere. And that's the surface area that we're trying to calculate, is whatever this is. So this is the area we need to calculate, right? So you've got this little region in the XY plane, but we want to go above that, cut out this section of the plane, and that's what we actually want the area of. Okay. And the way we calculate it is, well, we're going to use our formula here. So we're going to need a parameterization, smooth parameterization, but it will be. Then we're going to calculate this TU and TV, and then we're going to set up this integral, and then we're going to do the integral. It's actually not going to be that hard. Okay. So let's just think about the steps here. So our first step is going to be parameterize the surface. Okay. So this is a plane. It's given to us this way. And since z equals something, we know how to do it. We should just do x equals u, y equals v, and then z is just going to be the equation of that plane, but let's just replace the x with u and the y with v. So 4u plus 5v minus 5. Okay, so there's your parameterization. What about u and what about v for bounds? Well, they gave them to us, right? They gave us bounds for x and for y. X was supposed to be 0 to 3, and y is supposed to be 0 and 2, and we just replaced the x and the y with u and v, so we can keep the same bounds. Okay, so once you have that, we're going to need, that's not step 3, now we are going to need the tu and the tv, right? We are going to need these things. That's not that hard, right? We're just doing derivatives, partial derivatives. Okay, so we need to compute tu, which was vector with dx du, dy du, dz du, and then also tv, which is same thing, but with v. Okay, so those are going to be easy. So for us, tu is going to be the vector. Um, Derivative of x with respect to u is going to be 1. The derivative of y with respect to u is going to be 0. Right? I'm gonna write this out actually. So like d dx u, d dy, what? Sorry, let me rewrite these so that they make sense. ddu, they're all ddu. ddu v, ddu z, which is negative 4u plus 5v minus 5, right? So we're doing partial with respect to v of all of the components. So you get 1, 0, and negative 4. Okay, similarly, we're not going to write it out in as much detail. We're taking the partials with respect to v. So partial with respect to v of u is 0. Partial with respect to v of v is 1. Partial with respect to v of z is going to be 0, 5, and 0. So 5. Okay, so we've got that. Uh, they're constants because it was a plane. If there was a more complicated surface, they would not be constant. Um, but then we should be able to set up our integral, right? So our surface area, so set up integral, which is uh, integral over d of magnitude tu cross tv dA. The dA is going to be du dv. So we've got a double integral over the magnitude of 1, 0, negative 4 cross 0, 1, 5. The dA could be dv du or du dv, whichever way you want it. I'm going to do du dv, and we're going to put the limits in here as well. So what are our limits of u for u? 0 and 3. And the other one was 0 and 2, I believe. Right? And that's going to be our surface area. Okay, so there's your integral. Of course, we actually have to do this cross product. This is a good time to remember to use Wolfram Alpha. Um, Save yourself some time on these. Cross. There's a lot of ways to type this in. So I'm using parentheses right now um, because I'm lazy and I think it will understand parentheses as vectors. So I think these are our two vectors, 1, 0, negative 4, 0, 1, 5. Um, if this doesn't do a proper cross product, we will fix it. Okay, it did. Okay, so we got 4, negative 5, 1. Also, and take that and ask for the magnitude. So I'm too lazy to do even that. Square root 42. Okay, so at that point, we've set up our integral. So then we should be able to finish up our integral by integrating. So this is going to be an easy enough integral that even I can do it. I'm going to take the square root 42 out, du dv. So this is going to be square root 42, 0 to 2. Integrate du, you get u. from 0 to 3. That's going to be square root 42, integral 0 to 2, 3 minus 0 dv. That's 3. I will take the 3 out, have an integral from 0 to 2 of dv, which is v from 0 to 2, which is 2 minus 0 when we plug in the limits, and we get 6 square root 42. And this is an area, so I'm going to write unit squared. And that's it. So we just do the integral once we set it up. Okay, and that is how you do a surface area integral. So step by step. Parameterize the surface, calculate that TU and that TV, set up your integral, use Wolfram to do the cross product if you're lazy, which I am, and then finally integrate. Possibly using Wolfram again because I'm lazy. Okay, so here's another problem. This is another straightforward surface area integral. So same type, but not a plane this time. Find the area of the surface F defined by, they say defined parametrically by, but I'm going to say defined by, they go R UV equals, what do we got? Negative V squared minus 7I plus negative 7U plus 8VJ plus 8U minus VK. And they say 4, negative 2 less than U less than 0, negative 2 less than V less than 3. Okay, so we're just going to do our same tricks, but it'll go a lot faster this time because we know what we're doing now, right? So the first thing we have to do is parameterize, except that we don't because they did it. They did it for us. So the next thing we need to do is we need to compute the TU and the TV. Now remember what you're doing, right? It's x component, y component, z component with respect to u and with respect to v. So tu, I'll write it out this time again. I'm going to use triangular brackets again. So you're going to do partial with respect to u of negative v squared minus 7. That's your first component up here. Partial with respect to u, negative 7u plus 8v. And partial with respect to u, 8u minus v, right? Just making sure we know what we're doing. Do those partials. We're going to get 0, negative 7, 8. Okay, so we got constants again there. That's okay. We need TV. I'm not going to write it out again. But we can actually see what we're taking the partials with respect to. So actually, you know what? I said I wasn't going to, but I am because I just realized I can copy paste it. And then just change the U's to a V's. Okay. So let's do those partials. So we got negative 2v, 8, negative 1. Is that right? I think that's right. So at that point, we need to set up our integral. Double integral over d, du cross tv, dA. So I'm going to set that integral up, and then I'm going to do this cross product, and I'm going to do the cross product on Wolfram. And this is a good use of Wolfram because cross products take a little while to calculate. There's nothing special about them, but they take a while to calculate. So this is a good opportunity to do this. So I'm going to go cross. What's our first vector? 0, negative 7, 8. 0, negative 7, 8, comma. What's my second vector? Negative 2v, 8, negative 1. Wolfram won't care about putting variables in here. It'll do the cross product anyway. So I get this for my result. Negative 57, negative 16v, negative 14v. We need the magnitude of that, of course. And then we still have dA, which I haven't set up that integral yet. Um, so again, I'm going to take the magnitude. Easiest way to do that is to select your result. It brings it up to the box. And then I can say magnitude. 452. It says absolute value v squared, but that's v squared plus 3249. Okay, is there a simpler form? No, I guess not. Okay. Um, and then we need our limits of integration. So what are our limits of integration? I think those are given to us as well. U negative 2 to 0, v negative 2 to 3. So let's go negative 2, 0, negative 2, 3, and let's go du dv. I got those right, right? Yeah, okay, u is negative 2 to 0. Okay, I did them right. Okay, you know what? Let's do the integral. Let's just do the integral on Wolfram while we're here. Please let me scroll. Thank you. Um, Actually, let's go down here to where it said assuming v is real. Let me scroll. Thank you. Okay, here we go. Let's select that. That's what we're integrating. And first thing we're doing is we're integrating that, but that's a du integral, right? It's got v's in it, but we're doing a du integral from negative 2 to 0. Negative 2 to 3 dv. Move that over. Do we have a result? That is not what I wanted. Where's the answer? Oh, it's right here. So I did the integral. I got 2 integral 452 v squared plus 3249. Now we're integrating that from dv from negative 2 to 3. It didn't integrate it. So when it doesn't do that, then I try to write it with more verbs on there. Integrate. There, now it did. Um, and so it gave us this rounded to 2 decimal places. It gave us 651.45. Now, by the way, look at this answer here. They did hyperbolic sine. So the correct method to integrate this would have been trig substitution. So you do not want to do trig substitution on this. You really should use a computer to calculate this. They say to 2 decimal points. 2 decimal points is fine. Um, and if they don't need it exact, then do it on a computer. You'd be crazy not to. All right. So units squared. Okay, so that's how I would do these. If you can integrate it, just integrate it. But if it's weird, then you're going to do something like I just did. Okay. Yeah, we'll do one more of these, and then I think we're going to stop here and split this into 2 lectures. Um, so what have we got? They say find the lateral surface area of the cylinder x squared plus y minus 1 squared equals 1, bounded below by z equals y minus 6 and above by z equals y plus 6. Okay, what is going on here? This seems crazy. Yeah, this is nonsense. Okay, this is going to be annoying. We're going to do it though. Okay, so what are we looking at? So what's going on is this is a cylinder. It's just been shifted over one in the y direction, it looks like, one in the positive y direction. So it's like this. Okay. However, didn't they say bounded below by z equals y minus 6 and above by z equals y plus 6? So those are actually planes that are slanted like this. Like this is up at 6. And then this one slanted down this way. Um, and it actually, yeah, that's fine. And then the other one is down here. Trying to figure out how to draw this. Hold on. And goes up this way. Uh, that's terrible. But the point is that you're chopping the cylinder up so that it's like got a slanted top and a slanted bottom. That didn't help at all. Okay, so I think you get the idea though, right? So the top and the bottom are slanted because these planes are coming in and chopping it off at an angle up there. Um, okay. And so what you'd have to do is you would have to come up with the parameterization of this surface and appropriate limits of integration. So it's a little bit tedious. What they do is, first of all, this is an x squared plus y squared type of integral. So probably I want to try to do that. So let's parameterize this. Parameterize. Okay. So to start with, because I see the x squared plus y squared, I'm going to try um, that x is going to be like, what do they do? Oh, okay. So first they do this. They say, let's write this in polar coordinates to start with. So you have, which was going to be the same thing as we did. Actually, let me think about this for a second. If I do that, um, yeah, okay. So they did, I think we do want to do what they did. So this is your original surface. So they just, they go polar coordinates first. So x is r cosine theta squared. Y is going to be r sine theta, but we can multiply this out here. This is going to be like y squared minus 2y plus 1 equals 1. Um, but then r squared cos squared theta plus this is r squared sine squared theta minus 2r sine theta. And then it's plus 1 on both sides, but I'll just cancel those now. Cancel, cancel. And when we just get equals 0, this is theta. So we're here. This right here is just r squared because r squared cosine squared, r squared sine squared. So use the identity there. So you end up here. This tells you that r and then r minus 2 sine theta equals 0. So this says r equals 0 or r minus 2 sine theta equals 0, which is r equals 2 sine theta. Okay, so then what would we be doing here? Um, Trying to think. So this is our surface, but then what's the parameterization we're using here? Um, okay. So I think what's going on here is this. So I think they said this. Um, so like we were doing polar coordinates, right? So like x equals r cosine theta, y equals r sine theta, and then normally z just equals z, right? This is just polar. But then what we want to do is we've got this right here. So you take that surface, um, on the surface, r is 2 sine theta, right? So replace all of your r's with 2 sine theta. And you want to sub that in for that r and for that r. Okay? And when you do that, then you're going to get x is r, which is 2 sine theta, cosine theta, which is cosine theta. Y is r, which is 2 sine theta, and then sine theta. And then z is just z. So what you end up with here is x is 2 sine theta cosine theta, y is 2 sine squared theta, z equals z. And that's your parameterization. Okay, now what I would do here is we're getting used to using u's and v's, so let's just keep using u's and v's. So my parameterization is going to be exactly the same thing we have up above, but we're just going to switch the variables to u's and v's. So how about x is 2 sine u cosine u, y is 2 sine squared u, and z is going to be v. Does that make sense? We're just switching the theta to u and the z to v, just so we can keep using um, u's and v's. Okay, so having done that, another thing you might want to do, and you don't have to, um, let's see here. No, this is fine. Um, okay, this is fine. So we got this. So we parameterized it. Okay, what we don't know is about limits of integration, unfortunately. Um, like what's the, oh yeah, we do, I think actually, because we used, what is u? No, what is x? X is r cosine theta, y is r sine theta. Okay, so I think we want that in polar coordinates, I think, right? Let me see if we can figure that out. No, we don't want that. Okay, yeah, okay, I see. Okay, so this is fine for right now. Let's just say we're stopping here and we're going to go to the next step, which is going to be to calculate the TU and the TV. Okay, so you would calculate this however you want. TU is going to be the derivative of everything with respect to u. So you got a product rule up here for that sine u cosine u. So it'll be like 2 sine u derivative of cosine u is negative sine u plus uh, derivative of sine u is cosine u. So 2 cosine u cosine u. So you end up with 2 cosine squared u minus 2 sine squared u. Uh, yeah. And then your derivative here with respect to u is going to be chain rule. So bring the 2 down in front for sine u, derivative of what's inside, which is cosine u. And then the derivative of z with respect to u is 0 because there is no u. Now TV, partial with respect to u, v is going to be 0, 0, 1. So at least that one's easy. Okay, so we got the TU and the TV. I think you can use trig identity here, um, which, let's see here. If you use trig identities, then I'm just going to write these down rather than show you the identities. Um, this right here there's a trig identity says that that should just be 2 cosine 2u. And for sine u cosine u, this one is just uh, 2 sine 2u. Although you could just leave it the way it is, that's fine. And of course, that's 0. Okay, so that's just trig identities. We didn't do anything. All right, so we got these, and then we should be able to set up our integral. The limits of integration are going to be a little bit of trouble. So our integral magnitude tu cross tv, dA, we haven't decided the order of integration yet. But we can do this cross product. This again is where you want Wolfram alpha probably just to do the cross product for you. Not that it's hard here for this one. Hey, wait. Go away. The wrong one again. It switched the sides. Okay. We want to do the cross product of tu and tv. So we will. 2 cosine 2u 2 sine 2u 0 close. I should have opened 2 sets. Now I have. Close. Okay. First vector. There's an extra comma in there. Hold on. Next vector was 0, 0, 1, which actually makes the cross product not that much trouble, but you know, I gotta erase the words there. Try again. Okay. It did not, did it do the cross product? It did. Okay. And then we want the magnitude of this. Well, okay. That's nice. We like that. Um, so there's the cross product there. Did on Wolfram. Then we need to still set up the limits of integration. So what you're going to have to do is your variables are u and v, right? So what you're going to have to do is figure out what the appropriate or what the what the top and the bottom limits of integration are. So what they've got here is when we're integrating, z is just v, right? So what we need to integrate over, let me just draw the cylinder again real quick. Um, right, the top here was, I think they gave it to us. I'm looking at the problem. I'm not going to scroll up. But they told us that the top plane was z equals y plus 6, right? And the bottom was z equals y minus 6. But if we use what these things are in our parameterization, that top plane is z, which is v. Y, what's y? 2 sine squared u. I think that's right. And then the bottom one, v again, and then 2 sine squared u minus 6. And so if the top is this and the bottom is this, then we can say that v should be in between those. 2 sine squared u minus 6, 2 sine squared u plus 6. And then for u, what is u? So the variable u here was the u from polar coordinates, right? The u, what u was, sorry, hold on. U was the theta from polar coordinates, but we changed it. Um, okay, and so when you're integrating this, which you also have to remember where the axes were, um, the theta from polar coordinates is from, we're going from here to over here, which is u. Um, there's nothing on this side, right? Nothing on that side of the x-axis because of the way the circle was way up here, right? Oops, not what I wanted. Because of where the cylinder is. It's not at the origin. If it was at the origin, then you'd be looking at integrating for theta would have to go all the way around 0 to 2 pi, right? But it's not because this one is this circle right here, which I just accidentally erased. This one is 0, and then the opposite direction is pi. So to get this entire circle, you're just going from 0 up to pi. And that's for theta, but theta is v because we just changed the theta here to u. I said v, but theta is u. Okay, so what I'm doing is trying to say that. Okay, because of the side that, because of where u is, just on this side of the x-axis. So what you end up doing is that v, your v is going to go from actually 2 sine squared u minus 6 to 2 sine squared u plus 6. And then your u is 0 and pi. And that's kind of hard to set up, but that's what you had to do on this one. And your last step is you're going to integrate, which we're just going to do on a computer again because we are lazy. So we're going to integrate this on a computer. So what do we got? We're integrating 2 dv integrate, nope, integrate, move the cursor. Oh my God, I hate computers. Move the cursor, the cursor. No, move the cursor. Fine, we'll do it this way. So we'll see if it did the right thing here. If not, we'll put parentheses and stuff where they need to go. No, it looks like it did it right, right? So we get 24. Why does it do that? Move it? Yes, it's selected now. Work. Duplicate it. Don't delete it this time, computer. Thank you. Okay, dv. So what did we just do? Well, we did that first integral. So we ended up with the first one gives us 24, and then we got du. So we're integrating 24 du, which is going to, I mean, it's just going to give us pi, 24 pi. Okay. So, I mean, you could have done those integrals. So they're not going to kill you to do once they're set up. Setting them up was the hard part. But we didn't. We just did this. Okay, so I think that's going to be it for here because we're an hour and 25 minutes in. Um, what I do want to say is that we can go, like, the next thing we're going to do is just going to be this. So, next lecture, we're going to go from this, which we've just done. This is surface area. We're going to change that. We're going to do an integral of f ds. So that's a surface integral. And also we're going to do that kind. But there's not a lot to these really. I mean, we're just going to be setting up more integrals. Like you can already do the second kind, the middle kind here. Um, this is straightforward. You're just going to do exactly what we just did. You're just going to have a function there. That's it. Anyway, I will talk to you guys next time. Good luck on the exam stuff, studying. See you guys later.